Greetings, Physics 2001, Section 102 students. This is Lecture 23 on Thermodynamics, and it's the one that normally would be delivered on Tuesday, April 14th. So this is one of two lectures on thermodynamics. General organizational stuff. You can find any Q&A answers or links to Q&A and on the course webpage and PDF version of the slides, though presumably you've already found that, but in case you haven't, it's on the course webpage, so just click that link. There's a homework assignment due on Friday. Note it's called Assignment 13. There was no Assignment 12. That got canceled because of the pandemic. We basically cut some questions, reshuffled some things. So it's called Assignment 13, even though it's the 12th one that is due on Friday. Still have our pre-class stuff. And of course, the help room and SI are still happening via Teams, and you have an email from a while ago with the links to those team sessions. And you can do help room and office hours via email as well. Major organizational thing is we have exam 3 now. So remember at the beginning of the semester, there were 2 midterms and a final. We decided to create a third midterm to try to mitigate the damage done by any one exam. Given the transfer to the new format. You guys did great on exam 2, so maybe it wasn't necessary in retrospect, but we've done it. So we're going to have exam 3 on Lon Kappa. That is going to be open starting at noon on Monday, April 20th, and it will close by 6 p.m. on Tuesday, April 21st. Okay, so you need to complete it within that time window. Once you start, you only have 90 minutes to do it. Okay, just like the last time, and the 90 minutes needs to fully fall within the time window. So you need to start by 4:30 p.m. On Tuesday at the latest if you want to have your full 90 minutes to do it. Okay, so that's exam 3. It's going to be similar in style to exam 2. Technically, it's going to cover everything since the beginning of the semester, but really in practice, we're emphasizing the content covered since we returned from spring break. So basically anything that's been online, that is what's going to be emphasized on exam 3, and it's going to be material through fluids. So it is not going to cover any of the thermal physics. So basically rotation, simple harmonic motion, fluids, that stuff is what's going to be emphasized on exam 3. And there is a it's not really a link, I guess it's a link on Lon Kappa that's like information for exam 3. So go find that and it'll tell you about the format of the exam and the content that's going to be covered. Okay, so now I'll begin this actual lecture on thermodynamics. And as usual, we have kind of a summary of the takeaways from this lecture here. Okay, so thermodynamics, why is it useful? What are we doing? Well, you might be interested in what's the maximum efficiency you can actually get from an engine. So engines are not 100% efficient, and you might naively think, oh, we just need to design it better to increase the efficiency. Well, it turns out there's a theoretical maximum efficiency. You cannot go higher than, so we'll figure out what that maximum efficiency is when we cover thermodynamics. And you might be interested as far as why do the giant planets in the solar system, why do they still have hydrogen in their atmosphere, but the Earth doesn't really have hydrogen in its atmosphere? Maybe you're not interested in that. I think it's a cool question, and we will basically learn about why that is. Okay, so let's just do some definitions. So with thermodynamics, we're just going to be dealing with gases. So we're not dealing with all fluids. So a gas is a fluid that fills its container. Okay, so if I put a little bit of gas into a beaker, it will basically expand to fully fill the beaker. It's different than water because if I put water in a beaker, it only fills up to a certain height. It doesn't fill the entire beaker. So a gas is a fluid that fills its container. We're going to deal with so-called ideal gases, and that's fine because most of the gases you encounter in life can be treated as an ideal gas. So the ideal gas is low density, such that you really only have classical collisions occurring between molecules. So you have these like sort of billiard ball style collisions between our molecules. And like I said, the air we breathe is like this. Most of the gases you'll deal with um, outside of extreme environments are going to be well treated by an ideal gas. And we understand the ideal gas by considering microscopic interactions. So it's actually kind of fun to think about. We're going to basically begin from the billiard ball collision level, and we can then figure out the collective properties, if you will, the bulk properties of the gas, beginning with the consideration of these microscopic interactions. If we take a snapshot at any moment in time of our gas, then it's going to be in a state. That's how we call that snapshot. And so that's described by state variables. So the pressure, the volume, number of molecules you have, the temperature of the gas, its internal energy, its entropy. These are the state variables. We'll talk a bit more about entropy. It reflects the order of a system. So if you imagine, so if a toddler, so when my toddler takes his blocks and he stacks them up into a nice tower, that is a relatively low entropy system. It's quite ordered. When he takes the tower and yells the word tall and then smashes the tower over for some reason, it's a fun thing for him to do. The blocks are scattered all across the room, and that is a very disordered system. So there's a lot of entropy. So that's basically what entropy means. So we have a lot of particles in a gas, so we're going to define this concept called a mole. That way the magnitude of the numbers we deal with will be a little bit more manageable. So a mole is 6.02 times 10 to the 23 molecules. We define this number 6.02 times 10 to the 23. There's some more decimal places, but that's close enough, as Avogadro's number, as n sub a. Okay, so that's just known as Avogadro's number. And if you look at the periodic table, the numbers that you see under the element, so if you look at the periodic table, you see these numbers underneath the element. And so 13, 14, 15, this indicates the number of protons in that nucleus, or valence electrons, if you will. So number of protons that are in that nucleus. And then the bottom number here, this indicates the number of grams per mole for an atom of that element. Okay, so for instance, 28.09 grams of silicon gives you 6.02 times 10 to the 23 atoms of silicon. Okay, so the number of moles in an item is going to be just described by this lowercase n. And so it's going to be the number of molecules or atoms, depending on what we're dealing with, divided by Avogadro's number. So we're going to use Avogadro's number just to keep the magnitude of things more manageable because, for instance, if you only have 28 grams of silicon, that's not that much. That's already, right, more than 10 to the 23 atoms of silicon. So the numbers can get pretty ridiculous when you get to actual appreciable masses of items. So that's why this helps to keep it more manageable. So those are things that you need to know. Just write it down, that a mole is Avogadro's number of molecules and what the magnitude of Avogadro's number is. Okay, so let's use this concept of Avogadro's number, this mole, and figure out the mass of a molecule. So this is a little more complicated than the silicon case we mentioned a moment ago because there are multiple elements here. So what's the mass in grams of 3 moles of CO2? And you need to use the information on the bottom right-hand part of the slide. So these are the masses of these elements, and they're listed in atomic mass units, where roughly speaking, an atomic mass unit is 1 gram per mole. Okay, so then what is the mass in grams if you have 3 moles of carbon dioxide, CO2? So pause. I'm going to assume that you have worked through this and that you have come back. And then, whoops, you see that it's 132 grams is the mass of 3 moles of carbon dioxide. So how do we do this? Well, let's first figure out the mass per mole. Okay, so we have a single carbon, and so we're going to have a single carbon times the carbon mass per mole. we have 2 oxygens. That's what the little subscript down here means, 2 oxygens. So we're going to have 2 oxygens times the oxygen mass per mole. Now we're going to have to use the information from this table on the right. So carbon has 12 grams per mole, which we're just going to denote by this U. Oxygen has 16 per mole, and so then if we add these up, we have 44 grams per mole. And so then the mass of 3 moles is going to be 3 moles times the 44 grams per mole, and so therefore 132 grams is the mass of 3 moles of carbon dioxide. Okay, so that's just the basic accounting, how we count the amount of gas we have. So now let's get into some practical equations that help us relate the state variables. So for instance, the pressure and temperature in a system. Okay, so we have the ideal gas law. So this is, you've probably heard it before, PV equals nRT. And so what do we have here? P is the pressure, V is the volume, lowercase n is the number of moles, R is the ideal gas constant, and T is the temperature. You don't need to do this, but if you move the volume over to the other side of the equation, then you realize what this is saying is the pressure is the product of the density and temperature. So if you take density times temperature of an ideal gas, that gives you the pressure, which makes some sense because if I have a denser gas, presumably it should be able to exert more pressure on the container because you have a lot of stuff packed into a small volume. And if I have a high temperature, you should have more kinetic energy in your atoms, and therefore you should have a higher pressure. So it makes sense on that level, but you don't need to know that. You just need to know PV is nRT and what these variables mean. R, this ideal gas constant, is a constant, and it's 8.31 joules per mole Kelvin. Okay, an alternative form to write this is a little bit more fundamental, and it's PV is equal to capital N K sub B T. Okay, so this capital N is the actual number of molecules. It's not the number of moles, so we have not divided by Avogadro's number. And then this K sub B is the Boltzmann constant. It's a fundamental constant in nature. And it's just, as you'd expect, it's the ideal gas constant divided by Avogadro's number, and so it winds up being 1.38 times 10 to the minus 23 joules per Kelvin. The form that you need to know is the one up here. Okay, you need to know PV is is nRT. So this is the one that you need to know. This form down here, why I mention it is if you continue in science, you may find this form is actually more common, but for whatever reason, for introductory physics, we tend to do the PV as nRT. So some special cases for ideal gases. So the ideal gas law is general, but under certain circumstances, you can have different special case laws that apply, if you'll go with me on that. So let's say for your ideal gas law, if you have this equation up here, but let's say your pressure is going to be constant and your number of moles is going to be constant. Okay, so then you can ignore those, and then you can see, if you sit there and stare at it, you basically result in something called Charles' law. So Charles' law is that the ratio between the volume and temperature in a gas is constant. If you have an ideal gas and if your pressure and number of moles is constant, then the ratio between the volume and the temperature of the gas must be constant. So what does that mean is if you have a constant pressure and a constant number of moles, heating the gas will increase its volume. So let's say instead you have, so this is the different scenario, let's say your pressure can vary, but you have a constant temperature and a constant number of moles, then you result in Boyle's law. And again, it's if you stare at this ideal gas law long enough, you'll see that. So if if your temperature is not allowed to change and your number of moles is not allowed to change, then it must be that the product of the pressure and the volume in a gas is constant. So again, if you have constant temperature and constant number of moles, you get Boyle's law, and so pressure times volume must be constant. So then, if you squeeze an ideal gas into a smaller volume and you don't allow the temperature to increase or the number of moles to increase, then that's going to increase the pressure. So you need for these to use SI units for these equations. So we're assuming you're using SI units. You see that in terms of the ideal gas constant. The temperature here is in Kelvin, right? Our energy is in joules. And so you need to be using SI units. So for temperature, you need to be using Kelvin. For pressure, you need to be using Pascal, and the absolute pressure in Pascal, not the gauge pressure, okay? In principle, what you could remember all of these laws just by remembering PV equals nRT. So in principle, you could just write down these 2 bullet points here. However, I do, like technically 3 because you need the ideal gas constant. However, I do encourage you to write down these special cases because it can help you come up with a quick solution to a problem on an exam. So if you're talking about gases, and for instance, let's say we take a gaseous volume and we compress it with a piston, and we might tell you, hey, the temperature is not going to change and the number of moles isn't going to change, then you can immediately jump to Boyle's law and just use Boyle's law. So I think you really should write down these special cases at the bottom because they can be useful for a quick solution, even though, again, they're just special cases, and technically you only need the ideal gas law to get the job done. Okay, so let's work through some practice problems here. So let's consider we have 2 gas-filled cylinders. They have the same volume and the same temperature. So cylinder A is filled with oxygen. Cylinder B is filled with carbon dioxide. There's the same number of moles of molecules in each cylinder, but they're different gases, right? So in cylinder A, your molecule is oxygen. In cylinder B, your molecule is carbon dioxide, and so of course you're going to have a different mass per mole. So the question is, which cylinder has the greatest pressure? So pause. I'm going to assume that you've taken a moment, you've come back, and then you will realize that it's kind of throwing you for a loop. The pressure is the same in both of those. So you take a look at your ideal gas law. PV is nRT. You see no reference to the molecule type here. We only care about the pressure of the gas, the volume of the gas, the number of moles of the gas, ideal gas constant, and then the temperature of the gas. Nowhere in here do we mention what type of molecule we have. Nowhere in here do we mention the mass per mole. So this is true just for any molecule type. So we can solve for the pressure, nRT divided by volume. And in the question here, we've specified that the number of moles, the temperature, and the volume are all the same, and therefore the pressure is just the same. Okay, so you might just be wondering, well, okay, how much is a mole really just for everyday life? Think about that if you have a mole of any gas at so-called standard temperature and pressure, so that means you're basically talking about 1 atmosphere, and so your standard temperature and pressure, so that's 1 atmosphere, and oddly, standard temperature is 273 Kelvin, which is actually 0 degrees Celsius, so it's quite cold, but that's what STP means. If you have 1 mole of any gas at STP, that occupies about 22 liters. So think of a beach ball, basically. So a mole of gas at standard temperature and pressure is about a beach ball. It's not that different in terms of volume occupied if you're talking about room temperature. So basically, if you're thinking of a mole of gas, you're for ballpark purposes, you're talking about a beach ball amount of gas. Okay, so follow-up question here. Now maybe the molecule type, it might matter. So consider we have 2 gas-filled cylinders that have the same volume and the same temperature. So again, cylinder A is filled with oxygen, B has carbon dioxide, and now we have the same mass in each cylinder. So the question is, which cylinder has the greatest pressure? So pause, take a moment. I'm going to assume that you have come back after thinking about this one and you worked it out. And you'll see the pressure in cylinder A has to be greater than the pressure in cylinder B. So again, ideal gas law, it's going to apply for all the situations we encounter. PV is nRT. So both cylinders here, they contain the same amount of mass, but keep in mind that CO2 is heavier per molecule. So you need more mass to create a mole of carbon dioxide than you do of oxygen. Okay, so then for the same amount of mass, you're going to have fewer carbon dioxide molecules than you're going to have oxygen molecules. So cylinder B needs to have fewer molecules. It has a lower n, the lowercase n. So then if you have a fixed volume, a fixed temperature, and a lower number of molecules, lower n, then that means you have a lower pressure. Okay, so just simply thinking about this one, we have the same mass, but it takes more mass to make up 1 mole of CO2. It's a heavier gas. So for a heavier gas, then relative to a lighter gas, if you have the same amount of mass, you're going to have a lower number of molecules, and therefore, in this case, because you fixed all the other conditions, a lower pressure. So it's a lower pressure because we fixed the volume and the temperature. Okay, so one more question with our ideal gas law. So suppose that we triple the pressure of a gas, we double the volume, and we keep the number of molecules the same. What's going to be the ratio of the temperatures before you or after you did all this business to before you did all this stuff? So you have a gas, it has some temperature, you're then going to triple the pressure and double the volume. You're not going to change the number of molecules. By how much does the temperature increase? By what factor? So I'm assuming that you've paused and you have come back, and you'll see the temperature is 6 times higher. Okay, so again, ideal gas law, PV is equal to nRT. Our temperature, we can solve for the final temperature of the gas. We're just doing some algebra. So all we've done is we've divided the number of moles over to the other side and the ideal gas constant. And we're now giving subscripts to say the temperature of system B, right, is the pressure of, not system B, before. The temperature before is equal to the pressure before times the volume before, divided by the number of moles before. And we have the same thing for after. The temperature after doing all this stuff is equal to the pressure after times the volume after, divided by the number of moles after doing all this stuff. But we have defined in the problem that the pressure after doing all this stuff is 3 times higher. The volume is 2 times larger. The number of moles has not changed. Okay, so we will substitute in this after pressure, this relating after pressure and the before pressure, and relating the after volume and the before volume. We'll substitute that in to equation 3 here, and that basically we see then we have the before pressure times the before volume divided by before number of moles and ideal gas constant, which is just the before temperature, and then 2 times 3 is 6. So our temperature has increased by a factor of 6. Okay, so now let's move on to a different topic. So what we've covered so far is just basically how do we do molecule accounting, and then with your ideal gas, how are the state variables related? Now we can think about the system a little bit differently. So this is taking a more microscopic view of the gases, and it's called kinetic theory. So the reason it's called kinetic theory, right, is the kinetic should remind you of kinematics. So you're really thinking of physical motion of individual microscopic particles in the gas. So we're going to understand our gas properties in terms of the interactions of the microscopic constituents of the gas, so the motion of the atoms and or molecules bouncing around in there. So we assume that our gas molecules are like billiard balls. They're going to bounce off each other. They're going to bounce off of the walls of the container. And so if we have a really large number of interactions, okay, so we don't actually have to follow each individual particle and figure out what happened to it, and then go to the next one, each individual, and figure out what happened to it. We don't have to do that because we have a huge number of interactions, and so that's going to give these molecules similar average properties. So you're going to have an average kinetic energy for each molecule. On average, you're going to have some velocity, right? So if we take, for instance, a gas, let's just say room temperature, and we're going to look at the probability of having some velocity as a function of the velocity, you see that there's a big distribution of velocities for a room temperature gas. So there's lots of different velocities any given molecule could have, but on average, you have about 400 meters per second at room temperature. Okay, so then similarly, if you then increase the temperature, you have a really wide spread of velocities for your gas molecules, but on average, you have about 800 meters per second in this scenario when you've increased the temperature up to 1200 Kelvin. Okay, so we're basically going to say, look, let's think about this in terms of these average properties. We're going to treat this as microscopic particles, but then we're going to say, okay, let's just consider the average properties. If you want to get fancier and you move on to doing, if you, let's say you love this so much you become a physics major, then you will take into account these distributions to some extent. But for our purposes, we're just going to say, well, what's the average? That's what we care about. Okay, so for a given temperature, we can define this typical velocity, and we call it the root mean square velocity. So what it practically means is you would take all the velocities in a distribution, you'd square it, you'd figure out what the average of the square velocity is, and then you'd take the square root of that. That's the definition of the root mean square. So for and that's just what we're going to take as the quote unquote velocity of a molecule in a gas. It's really a kind of average. So it's our root mean square. So for a given temperature, the average kinetic energy of our molecule is going to be 1/2 mv squared, but here we're using the root mean square velocity. So the average kinetic energy is 1/2 mv squared, and we can determine this root mean square from the temperature by saying this kinetic energy, this average kinetic energy, is equal to 3/2 times the Boltzmann constant times the temperature of the gas. Okay, so that is true for our ideal gas. If we want to know what the average velocity, or roughly the average, it's really the root mean square velocity is of a molecule in our gas, when it's at a given temperature, we can use this relationship here. So this is the kinetic energy, average kinetic energy expressed in terms of temperature. This is the usual kinetic energy that we're used to from kinematics. And by defining this root mean square velocity, we can relate the two. In terms of the pressure, we can figure out the pressure times the volume in the number of moles by basically saying, okay, remember we had that PV is equal to capital NKT. We can now substitute what we know about the temperature because we've related temperature to root mean square velocity in this equation. And so then the pressure times the volume is equal to 1/3 times the total number of molecules. This is not the number of moles, total number of molecules, times the mass of a molecule, a single molecule, times the root mean square velocity squared. Okay, so these are equations that you want to know if you want to use information about the velocity of molecules in a gas to solve for things like temperature, pressure, or more often, if you want to figure out what the average velocity is given other information about the system. So if you know the gas's state variables, the temperature, or pressure, volume, number of molecules, then you can figure out the velocity using these equations. Okay, so that was kind of a lot, pretty new and sort of abstract. So let's do a kind of practical question. So you guys will potentially remember that when we talked about circular motion, we talked about gravitational orbits. And one concept with a gravitational orbit is that any object with some mass has an associated escape velocity. So that's the speed that's required to overcome the gravitational pull of that object. And so if you have a gas in an atmosphere of a planet, right, that each molecule in the gas will have there's going to be an average velocity that the molecules in the gas will have. That average velocity is going to depend on the mass of your gas, of course, and the temperature of the environment. And so the question is, which type of gas is most likely to escape from our atmosphere? So let's say you started out with hydrogen, helium, neon, xenon. You had all those in a bottle. You open the bottle. Of course, they're going to mix around in the atmosphere, but which gas is most likely to actually escape, totally leave the planet? So I'm going to assume that you've paused and you have come back, and you will see that it is hydrogen. Now, I don't want you to make the mistake of thinking, oh, that's because hydrogen is a lighter gas, it's less dense, it'll rise to the top. No, this is different. This has nothing to do with buoyancy. This is truly the molecules have a higher average speed and they literally can escape the planet. It's not that the hydrogen's floating on top of the rest of the atmosphere. It's that the molecules are literally rocketing out, basically. Okay, so our average kinetic energy is 3/2 kT, and that average kinetic energy can also be expressed in terms of the typical equation for kinetic energy of an object, so 1/2 mv squared, where the v, the velocity, is the root mean square velocity. So if we have a given atmospheric temperature, then all of our molecules are going to have the same average kinetic energy. So if I release a bottle of hydrogen, helium, neon, xenon into the atmosphere, an average xenon molecule is going to have the same kinetic energy as the average neon, as the average helium, as the average hydrogen. They'll have the same average kinetic energy. But here we care about the velocity, right? So if your kinetic energy is roughly the same, but your mass is lower, then that means your velocity must be higher for that given molecule. So a smaller mass is going to lead to a larger velocity. So therefore, hydrogen is most likely to escape. And so that's where this fun plot comes in. You can plot the escape velocity of a given planet, indicated by the different circles here. So the escape velocity of Jupiter, for instance, is 60 kilometers per second. And you can then plot that versus the temperature. And so, for instance, we have Earth is situated here, so the escape velocity versus the temperature. And then what the colored bands tell you is which molecules will have a average velocity that is larger than the escape velocity of that planet. So, okay, so at a given escape velocity and temperature, you'll see, well, hey, helium tends to have this velocity on average. So if we go over to Earth, you see that if you go to Earth's escape velocity it's about 11 kilometers per second. And the temperature of the Earth, right, is about 290 Kelvin or so. And on average, your helium will have a little bit higher velocity than that at that temperature. So helium escapes, hydrogen escapes. All this other stuff is trapped. So lucky for us, right, water vapor is trapped. We're good to go. You can see that Mars, however, with its current temperature, it cannot hold water vapor. The water vapor will escape. Similarly, with the moon, basically you can only trap xenon on the moon. So even carbon dioxide, oxygen, they escape. Next time you're reading any sci-fi and they talk about terraforming, right, transforming a planet to support life, and they bring up some hocus pocus about introducing an atmosphere, that's all well and good. You can introduce an atmosphere. You can introduce or remove greenhouse gases to make the atmosphere warmer or colder, but you can't change the escape velocity of a planet. So you can only trap the gases that you can trap. Okay, so there are laws of thermodynamics that we should cover. So now we're moving into the thermodynamic considerations. So what we've done so far is we've taken a more microscopic picture. We've defined how many atoms we have. We've related the state variables of those atoms. We've thought about the little microscopic motions going on. So now we're going to deal with bulk properties. So this is really a thermodynamic picture, and it's different than what we've talked about so far. Okay, so I'm going to give an overview of the laws of thermodynamics, and then we're going to step through them, step through some of them. Okay, so the 0th law of thermodynamics, this just says that two systems are in equilibrium with a third system. If two systems are in equilibrium with a third system, then they're in equilibrium with each other. This is basically just the definition of temperature. Okay, so if temperature A is equal to temperature C, and B is equal to C, then A is equal to B, right? This is like your I don't know, elementary school logic. The first law of thermodynamics that we'll go more into in a moment, this says that when a system absorbs or emits energy, then the internal energy of the system changes accordingly. So energy can be absorbed or emitted via work, heat, adding or removing matter. If you do any of those things, then the internal energy of the system will change. So this is really a statement of energy conservation, but it is a very practical thing for us to use. So we're going to use this to define an equation that's going to help us solve some interesting problems. The second law of thermodynamics is that the entropy, so aka the order of a system, of an interacting system, increases. So what's the consequence? It's, for our purposes, one of the main consequences is that heat does not spontaneously flow from a cold object to a hot one, and it never will. So qualitatively, where do I get that from? Well, for a cold object, microscopically, your molecules are not going to have that high of a velocity. They're going to be moving around more slowly. So if you think of how many physical spatial configurations you sample with time, it's many fewer for a cold system as opposed to a hot one. In a hot system, you have a rather high motion, or rather high velocity rather, of your molecules. And so over a certain span of time, you will sample many spatial configurations. So then the hot system has a higher entropy. And so then if these two systems interact, you're going to tend to increase the overall entropy. And so that means that the heat's going to flow from the hot object to the cold one. Okay, the third law of thermodynamics is that the entropy of a system approaches 0 at 0 Kelvin. So 0 Kelvin is absolute zero, the lowest possible temperature you can have. The consequence of this is actually very important, and we'll go over it at a later time. So the consequence is that engines have a limited maximum efficiency. Okay, so you cannot have a perfect engine. Okay, so since you need an engine to do any cooling, you cannot cool something to absolute zero. Okay, so one of the upshots from this is you cannot get more energy from a system than you put in. So there's no such thing as a so-called perpetual motion machine. So you got to get the energy from somewhere. Okay, so the entropy, it has to increase, and yeah, you wind up having a maximum efficiency of an engine. One thing I briefly want to comment on is you'll sometimes see floating around the internet things saying like the Big Bang violates the third law of thermodynamics, or maybe the second law, I can't remember. I have no idea what they mean by that. I think that the concept is that, well, if you started out with this very ordered system and then it spontaneously becomes disordered, how do you do that? I don't really understand that, because that's exactly what the law of thermodynamics say, that you start out with this really ordered thing, you go to a disordered thing, it expands. Their question might be, well, wait a second, how did you get this very ordered system to begin with? And the answer is, nobody knows, dude. That's like the Big Bang is more or less the beginning of physics. When you go before that, people have worked on it, but it's almost philosophy at that point. So at that point, we don't need to worry about which laws apply, because none of them, right? At that point, you're actually so compressed, nothing you've learned applies. Gravity doesn't work anymore. You have to get to quantum gravity. So you have way bigger fish to fry if you're talking about trying to go before the Big Bang. That's just an aside. Getting back to what we're actually supposed to be covering, thermodynamics. So let's work through the math of the first law of thermodynamics, and this will be practical for us to some extent. Okay, so remember, when a system absorbs or emits energy, the internal energy of the system changes accordingly, right? So this is our statement of energy conservation. So if we define U as the internal energy of a system, Q is going to be the heat added to the system. So if we remove heat, it's minus Q. And work as the energy done by the system. So if it's minus W if work is done on the system. Then we have the change in internal energy of the system is equal to the heat added to the system minus the work done by the system. Okay, and this is very important, that the change in energy of the system is equal to heat added to the system minus work done by the system. So if instead work is being done onto the system, you need to change that to a positive. If instead heat is being removed from the system, you need to change this to a minus Q. So that is important. So for instance, let's take scenario A here. We add heat to our system and work is produced. Well, we've added heat, so positive Q. System's done work, so positive W. And so we use this equation here. If instead, let's go to scenario B, where we're doing work onto our system, and we're adding heat onto our system, then in this case, right, that work is not being done by the system, it's to the system. So we have to change this to a minus W. So then that would make this a plus sign, right? You have minus minus W. And then in this case, in B, we're adding heat to the system. And so Q here will still be positive. So for scenario A, we have, we'd take the Q minus W. For scenario B, we'd take Q plus W. Okay, so this equation is always true. It's the change in internal energy is equal to heat added to the system minus work done by the system. And that's where you always have to be really careful. Is work being done by the system or on the system? Is heat being added or removed to the system? You have to be very careful here within the sign of these variables. So the system here, right, just as usual, is everything that we care about, and the surroundings is everything else. Okay. So let's just go ahead and do a question using this equation that comes from the first law of thermodynamics. So we have a system that contains a half a mole of diatomic nitrogen, so that's N2, so two nitrogen atoms stuck together to make a molecule. We have half a mole of diatomic nitrogen gas placed over a hot plate, so that's going to add 3,000 joules of heat into the system. At the same time, our surroundings are going to compress the gas. So that does 1,500 joules of work on the system. So then what is the change of internal energy of the gas in the system? So pause. Assume that you've paused and that you have come back. And you will see that the change in internal energy of the gas in the system is 4,500 joules. So we have our delta U is Q minus W. But remember, Q is heat added to the system. W is work done by the system. So here we have added to the system, we would have added 3,000 joules, so Q is just going to be positive. But W in this equation is work done by the system. We've done work on the system, so it's minus 1,500 joules that we plug in for W. Okay, so therefore our change in internal energy is 3,000 joules minus negative 1,500 joules. So that's 3,000 joules plus 1,500 joules, which is equal to 4,500 joules. So this is where the sign of Q and W really matter. You have to pay attention to those. Okay, so now we're going to take this equation from the first law of thermodynamics, that delta U is Q minus W. Change in internal energy is heat added to the system minus work done by the system. And we're going to then be able to learn something about how the system changes using so-called PV diagrams, or pressure versus volume diagrams. Okay, so when we transition between states on our PV diagram. So remember, a state is your system has a defined set of conditions. So it's a snapshot of that gas in time, has a defined pressure, temperature, volume, number of molecules, internal energy. If you change any one of those, you have changed the state of the system. Okay, so if you change from one state to another, that's a transition. So if just your pressure changes, that's a transition. You've transitioned from one state to another. If pressure and temperature change simultaneously, that's a transition from one state to another. So a really common way and a useful way to understand or to look at transitions is going to be using a diagram, and it's a graph that represents the pressure and volume of the different states of your system. Okay, it's called a PV diagram. So you'll start out with some, for instance, initial temperature, or pressure and volume, some state, state A. You undergo a transition, you wind up at state B. So this is what the PV diagram looks like. When you wind up at state B, you have a new pressure and a new volume. Okay, so if you transition from one state to another and back, that's called a cycle. So it doesn't matter how many intermediate states I have. If I begin at some state and I meander around this diagram and I wind up back at the same state, that is called a cycle. And that's interesting because if we want to understand engines, we need to use these cycles. So for a full cycle, your change in internal energy is 0. Makes sense. You wind up at the exact same conditions you started at. So if you go through a full cycle, your change in internal energy is 0. That is a useful thing to know, to write down, to consider as a candidate for your next tattoo. For a full cycle, change in internal energy is 0. Okay, so why do we care about these PV diagrams? So you can figure out the work done by or on a gas using the PV diagrams, which is kind of cool. And again, it sort of brings us closer to understanding engines. So recall that your work is a force times a displacement. So displacement is delta x. And you can recall from when we did fluids that the force from a gas is equal to the pressure times the area. Okay, so if we consider this picture on the right here, just a simple case of a piston, then the work done by a gas pushing up the piston is, again, work is force times displacement, but we can plug in for force pressure times area. So then we have pressure times area times displacement. Well, if I have an area times the length, that's just a volume. So the work is equal to the pressure times the change in the volume. So if the pressure is constant, then that is called an isobaric transition. So you have to be very careful. What I encourage you to do is to create a table of transitions. I'm going to refer to several different types of transitions, and what you should do is probably write down the name of the transition in one column. In the next column, what are the assumptions that are made that basically define that transition? And then in the third column, what equations do you use? So if the pressure is constant, we have an isobaric transition. That's what isobaric means. And so then the change in internal energy is equal to the heat added to the system minus P times delta V, because we've substituted in work done by the gas. Here, we've substituted in P times delta V. So this is only true if the pressure is constant. So that's only true for an isobaric transition. Can you make this nice little substitution? Okay. So on a PV diagram, if we can calculate the work then by integrating the area under the curve. This is going to be true generally, but it's very clear, I think, for this isobaric transition. So this is always true. You can get the work by integrating the area under the curve, but it's very convenient to understand for this case. So if I start out in some initial state with some pressure and volume, I keep the same pressure, but I increase the volume. Then I have P times delta V. So P is the height, delta V is the length. So then if I take the length of the square, or so the height of the square times the length, or however you want to refer to the two sides, I multiply the two sides by each other, that gives me the area under here. Well, pressure times the change in volume, that's the area here, right? It's the same thing. So pressure times the change in volume for an isobaric transition, that's the work. And so therefore the area under a curve in a PV diagram is the work. So you can calculate the work by integrating the area under the curve, which is pretty amazing. And that is just generally true on PV diagrams. So this just holds true in general. You don't have to hold constant pressure. So for instance, take this picture on the bottom left. I start out with some pressure and volume, and then I decrease the pressure and increase the volume and wind up with B. If I integrate the area under here, that is the work done by the system going from A to B. Now, an important point is if I go from B to A, then I have a negative change in the volume, and so that's negative work, right? That's work done onto the system to go from B to A. So it matters. So the area under the curve is the work, but if you're integrating, if you're basically moving from left to right, it's positive work. If you're moving from right to left, then that's negative work. So you can solve this for more complex problems by basically integrating graphically if you want to. So what we could do in this case here, we could treat little sections here as little rectangles. That's something called a Riemann sum. And we could do this P times delta V that way if we don't know the actual function. Or if you have these multi-step cases that are a little bit simpler, you could solve for the work in one section and then the work in another section and then add it all together. Okay, so let's put this into practice. So which of the following PV diagrams corresponds to negative work done by the system? So that's work done on the system practically. So which of the following PV diagrams corresponds to negative work done by the system? So I'm going to assume that you have paused and you have come back. And basically what you're looking for is when does the arrow go from the right to the left? When do I start out at a larger volume and wind up at a smaller volume? And if that is the case, then you're talking about negative work done by the system. Okay, you have to do work on the system to compress the volume, basically. So the work, right, is P times delta V. If the gas is expanding and the volume is increasing, it's doing work. If the gas is contracting, so the volume is decreasing, then work is being done on it, which is also referred to as the gas doing negative work. And D and E, these are the two that are contracting, so we've done some negative work here. Okay, let's work on another practice problem here. So we have three different transitions. So in each case, we are starting at A, state A, and winding up at state B. But we either do it via transition 1, 2, or 3. The question is, for which transition is the work done by the system the greatest? So I'm going to assume that you have paused and come back. And you'll see that it is transition 1, the work done by the system is the greatest because the area under the curve is the largest, right? It's the area under the curve in a PV diagram. And when I say the area under the curve, you're really figuring out all the area from the initial state, that whole line for your transition, down to the origin, down to zero pressure. You're integrating this whole region in here. And there's much more area under the curve for transition 1 as opposed to 2, and then 3 has the least area under the curve. Okay, so each transition goes between the same pair of states. So it's important to note the change in internal energy here is the same, regardless of which transition you use. We can use our first law of thermodynamics. Change in internal energy is heat added to the system minus work done by the system. So then our heat added to the system, that's the change in internal energy of the system plus the work done by the system. And so therefore, transition 1 also must have the greatest amount of heat added to the system, right? Because your change in internal energy, your delta U, is just defined by the change from initial to final state. You don't care how you got there. So for all three transitions, delta U is the same, but we established the area under the curve is greatest for transition 1. So the greatest work done by the system is for 1. So for these three transitions, if delta U is the same, but W is bigger for 1, therefore the sum is greater, and you had to have added the most heat to the system in order to do transition 1. Okay, so now we have another transition. We did isobaric. This is another one to write down in your table. So this is an isochoric transition. So isochoric, it means that you have a transition with no work being done. Okay, so a nice simple example is on the right. The volume has not changed, just the pressure has increased. So for instance, if you heat a sealed container, your volume is not going to change. Just the pressure is going to go up. So if your delta V is 0, then the work must be 0, is pretty apparent, I would say. And so then your change in internal energy, right, is the heat added to the system minus the work done by the system. The volume is fixed, there's no work done, so therefore the change in internal energy is just equal to the heat added. These are true for isochoric transitions. So again, take your table, write down the name of the transition in one column, isochoric. In the middle column, write down the assumption, that means no work, which also means delta V is 0. And then in the final column, therefore, the change in internal energy is equal to the heat added to the system. This is only true for isochoric transitions. Another transition, isothermal. So isothermal means there's no change in the internal energy. Okay, so for instance, let's say we have a gas container, we've slowly compressed it. Work is going to be done without heating it up. So you're very slowly compressing this thing. So for this transition type, the change in temperature is going to be 0. That's the definition of an isothermal transition. So then the change in internal energy is going to be 0, right? Sorry, I guess I said that wrong. Isothermal means change in temperature is 0, but also that practically means the change in internal energy is 0. Okay, so therefore, your heat added to the system minus the work done by the system is 0. So then your work done by the system is directly equal to the heat added to the system for our isothermal transition. Okay, so all the heat added it goes into work being done by the gas. Okay, so this is only true here for isothermal transitions. So again, you need to take your table. Isothermal transition is in the left column. The middle column says that means delta U is 0, that means delta T is 0. And then your rightmost column says, okay, the consequences of that are that for an isothermal transition, the work done by the system is equal to heat added to the system. Okay? And an example is shown in this PV diagram here, right there in the bottom right. Okay, the last type of transition that we're going to cover is an adiabatic transition. So I guess that means you have, let's see, you have isobaric, isochoric, isothermal, and adiabatic. So that's your 4 transitions that are going to be in your table. So an adiabatic transition means that there's no heat transfer. So if we do work on a thermally isolated system, heat is not going to be transferred, but the internal energy is going to change. So how do you do it in a thermally isolated system? You could imagine compressing a liquid inside of a thermos. Right? A thermos is basically thermally isolated. Or a star out in space is pretty much thermally isolated from everything else because space is a vacuum. Okay, so for this transition type, there's no heat added to the system, there's no heat removed from the system. That's what we're talking about, no heat transfer. So Q is 0 for an adiabatic transition. So then the change in internal energy is therefore going to be equal to minus the work done by the system. So for an adiabatic transition, work done by the system is equal to minus the change in internal energy of the system. This is true for the adiabatic transitions. So take your table, leftmost column, adiabatic transition, middle column, that means Q is 0, right column, that means the work done by the system is equal to minus the change in internal energy of the system for an adiabatic transition. So all the work done on the system changes the internal energy, okay? Or basically only changes in the internal energy allow the system to do any work. So this can sometimes be a really good approximation for a really fast transition because there just hasn't been any time for heat exchange. And it's great for the expansion of a supernova remnant. So this is something that a project that my student, grad student Shiv and I are just about to publish. It's under review now, and we basically use this approximation, this adiabatic expansion approximation, to study the elements that are made in a core collapse supernova. So this is actually a very practical approximation if you think astrophysics is practical. Okay, so that is it for this lecture. We'll finish thermodynamics with the next lecture, and then the following week's lectures will just be review for the final exam. As usual, please email me any questions that you have, and I will put the question and answer in a Google Doc. If you go look at the Google Doc and it's blank, that means there were no questions, which of course is fine, but keep in mind, if you have a question, somebody else does too, so do please ask it. All right.